हेलो एवरीवन, ए वेरी वेरी गुड इवनिंग ऑल ऑफ यू। कैसे हैं सब लोग? प्लीज गाइज डू जॉइन मी फास्ट so that we can start our session on time. This is Chandrashekhar welcoming you all to the India's largest, the best and your favorite live learning platform, that is BYJU'S Exam Prep. First of all, please do let me know if I am completely audible and visible to everyone. Please respond through the comment section, those who are watching me live, so that we can start the session. This is the practice session for the second law of thermodynamics. The theoretical part, the conceptual part we have already covered yesterday at 8 p.m. I hope you have enjoyed that session and you have tried some numericals as well on your own. If anybody is having any doubt in any of the concept related to second law, please do let me know. Otherwise, we will have the practice, numerical practice. I have brought the wonderful questions from the second law of thermodynamics, which you can expect in your examination. Hi Ranbir, good evening, welcome. How are you? What's up? Ki hal chal? कैसे हैं सब लोग? You guys are watching me live through the series which is for GATE 2023 aspirants. That is Mastering Concepts for GATE 23. For those who are meeting me for the first time, let me quickly introduce myself. My name is Chandrashekhar. I am a mechanical engineering graduate from IIT Delhi. I graduated in 2006 and I have also cleared engineering services examination in 2009. And from last 9+ years, I am completely into teaching, guiding the students who are preparing for various competitive examination, whether it be GATE, IES or any other PSU. So do respond through the comment section. Those who are watching me live, I can see people, but do not be mute spectator, because the more you involve yourself, the more comfortable you become with the subject, as well as you will enjoy more this session. Shall we start? Do not forget to like, share and subscribe the channel, because it is going to help you to get the complete solution for all your competitive examination. We are providing you the complete strategy, complete solution, everything, whatever we can help you with, we will be providing. All the syllabus, all the important topics, as well as the important concepts which you can expect in your examination. So do not forget to like, share and subscribe our BYJU'S YouTube channel, Hindi as well as the English channel. Yes. Hi Tushar, welcome. अच्छा, बहुत अच्छा लगा आपसे मिलके. Please keep your pen, paper and calculator. That is very important because it is the numerical practice session. And you should try on your own without any help, without any notebook, without any notes, without any reference book, so that you will come to know whether you will be able to recollect the concept, you will be able to apply those concepts within the minimum time frame or not. That is what you are going to learn from this session. All right. So this is our schedule for GATE 2023 aspirants. So for thermomechanical, the subject thermodynamics is going on, and every alternate day I am meeting live on the YouTube channel at 8 p.m. So next class will be on Wednesday and we will start talking about the entropy. Yes, gold life motivation fact. पूरा syllabus तो यहाँ पे नहीं हो पाएगा, but most of the important topics which are generally coming in examination GATE, these topics we will definitely cover here itself. So we will try to cover most of the subjects, almost all the subjects, but in each and every subject we will not be able to provide the complete syllabus. We will not be able to provide you the complete syllabus because of the time constraint, but definitely we will be providing you the topics which are frequently asked in your GATE examination. All right. This is the complete schedule for thermodynamics, basic and applied thermodynamics. So the basics and first law we have already covered. Second law, theoretical portion we have already covered. The next topic will be entropy, and then we will talk about the application of thermodynamics. These 4 topics are the most important in your thermodynamics syllabus, whether it be GATE, IES or other PSU examination like BARC, ISRO. You will find most of the questions coming from these topics only. So that is how we have designed this series, so that you will be having the concept clarity. At the same time, you will be able to solve the numericals. You will be able to develop the thinking process, thinking ability to solve the numericals, to apply the concept to the numerical questions. That is the idea behind having this series for GATE 2023 aspirants. All right. So stay with us till the end of this series. You will definitely feel the improvement. You will definitely feel the improvement in your confidence level. You will feel the improvement in your understanding level. So that once you will be having the clarity about the basic understanding about the subjects, you will be in a position to do the self-study for the remaining topics, because the other topics are not that important from the examination point of view, but they are interconnected with the topics I have brought here. And the last session will be Menti session, complete thermodynamics as well as applied thermodynamics. We will have a quiz on Friday, 25th March. So keep on revising those topics also, keep on studying those topics also, which I am not able to cover over here. All right. चलिए start करते हैं without any delay. Keep your pen, notebook and calculator so that you should be able to give me the answer before I give you the hint. Right? So there are around 12 to 13 questions in total, and the time duration is 45 minutes. Will we be able to cover these 12 to 13 questions within 45 minutes or not? So your dedication, your efforts will be definitely required to complete the session within 45 minutes. So let us start. Please make some noise. Those who are watching me live, please do make some noise so that we can start with our first question over here on the screen. I want everyone to give me the answer. Yes. Read the question and do let me know the answer. There are 3 engines A, B and C operating on Carnot cycle. That point is very, very important. And using the working fluid as argon, oxygen and air respectively. Engine A is having argon, engine B is having oxygen and engine C is having air as the working fluid. What is the correct answer? Yes, Sagnik, very nice. Others, Ranveer, good. Now look, Carnot cycle means a reversible cycle. Carnot is a reversible cycle, most efficient reversible cycle. So when the engines are working on reversible cycle, then the thermal efficiency of reversible cycle is a function of source and sink temperatures only. That is Carnot principle, that we call it as Carnot theorem or Carnot principle. Theorem or Carnot principle. According to Carnot theorem or Carnot principle, the thermal efficiency is not a function of, for a reversible cycle, thermal efficiency is not a function of working fluid. But actual cycle is having the actual cycle, if it is irreversible cycle, then the working fluid also comes into picture for real cycle. So the answer to the first question, Varun, it is not A, it is not B, it is not C. The thermal efficiency of all the reversible cycle will remain same. because all are reversible cycles, the thermal efficiency will remain same. And the same concept applies to COP for heat pump and refrigerator also. The same concept is applicable to heat pump. For a heat pump, COP for a heat pump or a refrigerator, if the cycle is reversible, then it is also having the variation with the temperature only. Whether it be COP or thermal efficiency. For heat engine, we talk about the thermal efficiency because it is work producing device, and for heat pump and refrigerator, which are work consuming devices, that is why we define COP to be the performance parameter. Is this clear to everyone? Is it all clear? Answer to the first question is option D. The next question, question number 2 on your screen. Read the question and try to solve it. Again, Carnot cycle. Whenever the word Carnot or reverse Carnot, the Carnot means reversible. Carnot cycle or reverse Carnot cycle, they are completely reversible cycle. So the Carnot cycle is having an efficiency of 0.75. One more thing, do you know? The efficiency of Carnot cycle, that means the reversible cycle, is given as 0.75 if the temperature of high temperature reservoir, that is the source. How the heat engine cycle can be drawn? That is the heat engine. Here is the high temperature source, and there is a low temperature sink, and it is producing work. Clockwise cycle is heat engine cycle. So this is source, high temperature reservoir is the source, and the low temperature reservoir is the sink, Q1, Q2 and W. That is how we have drawn the heat engine cycle in yesterday's session. So what is the answer to question number 2? I want everyone to get me the answer. So thermal efficiency is actually net work output upon heat input. Total heat input is Q1, work output is W, and from the first law of thermodynamics, we can say Q1 is equal to W plus Q2. So we can say W is equal to Q1 minus Q2. That can also be written as Q1 minus Q2 upon Q1, or we can write it as 1 minus Q2 by Q1. And because this is the expression for thermal efficiency for all the cycle, reversible as well as irreversible. But for reversible cycle, one more concept we have discussed. If it is a reversible cycle, Q1 by Q2 or Q2 by Q1 is equal to T2 by T1. So for a reversible cycle, we can say thermal efficiency is given as 0.75. That can be written as T1 minus T2 upon T1. From here, we can find out the temperature of the temperature of the low temperature reservoir or sink. The word sink could have also been used. Low temperature reservoir is the sink here, and high temperature reservoir is the source. High temperature reservoir is the source. What is the answer? Now, one more important thing you should take care of. T1 and T2 must be absolute temperature. Here T1 and T2 must be absolute temperature. What is the meaning of absolute temperature? What is absolute temperature? Absolute temperature means the temperature must be in Kelvin. That is the absolute temperature. So whenever we do the subtraction, whenever we talk about the difference of temperature, it does not matter whether you calculate the difference in Kelvin or Celsius. The question is to find out T2 na? Low temperature. So T1 has to be taken in Kelvin. What is temperature in Kelvin? How to convert? That is temperature in degrees Celsius plus 273. That is how conversion will be done. If you want to convert degree Celsius temperature into Kelvin, you should add 273. So T1 will be equal to, here T1 will be equal to 727 plus 273, that is equal to 1000. Is it 1000 Kelvin? And you can find out 0.75. 0.75 is equal to 1 minus T2 by T1, that is 1000. T2 you will get in Kelvin, and to convert it into degree Celsius, temperature in degree Celsius is equal to temperature which we are getting in Kelvin minus 273. That is how you will get the answer. What is the correct answer? Yes, Sagnik. What is your name? Gold life motivation factor. Fact. The correct answer is option B. Yes, great. Is this clear to everyone? The correct answer is option B. The next question for you guys. The next one. For a heat engine operating on the Carnot cycle, the work output is 1/4 of the heat transferred to the sink. Sink is low temperature reservoir. Sink is the low temperature reservoir. So if we draw the Carnot cycle, this is Q1, this is Q2, heat rejected is Q2, and the work output is W. This is heat engine cycle. High temperature reservoir is the source, low temperature reservoir is the sink. So the work output is 1/4 of the heat transferred to the sink. Do you understand this? This is statement. So W is equal to Q2 by 4, isn't it? It is not Q1 by 4. W is equal to Q2 by 4. And what is Q1? From the first law of thermodynamics, what is Q1? Q1 will be equal to W plus Q2. That is the first law, energy conservation law for the system. Heat entering, energy in is equal to energy out, because it is a thermodynamic cycle. So Q1 will be equal to Q1 by Q2 by 4 plus Q2, that is 5 by 4 Q2. Put the value. The thermal efficiency, whether it is reversible or irreversible cycle, the thermal efficiency is given by the net work output upon total heat input. So W is Q2 by 4 and Q1 is equal to 5 by 4 Q2. So it will be 1 by 5. Isn't it 1 by 5? That is 20%. A will be the correct answer. A is the right answer. Yes. Others, Ashish, yes. Others have not responded except Sagnik. Yes, Ashish. Hi, Abhishek. What's up? Let us move to the next one. Question number 4. This is beautiful question. This is very, very beautiful and important. The basic concept, whether you are clear with the basic understanding or not. Can you let me know the answer to this one? A reversible heat transfer demands. Do you know that heat transfer process is an irreversible process? Heat transfer is irreversible. Because why heat transfer is irreversible? Because heat always flow from high temperature to low temperature without any external work. Heat always flow from high temperature to low temperature without any work. If T1 is greater than T2, the direction of heat flow will be from 1 to 2. And if we want the heat to flow from low temperature to high temperature, we need to do external work. If we want the heat to flow from low temperature to high temperature, then we are supposed to do some external work, T1 and T2. Then external work needs to be done. Then external work needs to be done. That is why the process is not a reversible process. But in our Carnot cycle, the heat transfer is a reversible process. How the heat transfer becomes the reversible process? If the temperature difference is infinitely small. If the temperature difference is infinitesimally small, or the temperature gradient is infinitely small, then the heat transfer becomes a reversible process. For an example, in a heater or in a geyser, water heater. In case of water heater, what happens? If we talk about a water heater, there is a water and there is a heating coil. So the temperature of heating coil is almost same as temperature of water. The temperature of the heating coil is slightly higher than the temperature of water, then the heat will flow. Then the heat will flow from the heating coil to the water. Then the temperature of water becomes equal to temperature of coil. Then what happens? Then the temperature of coil further increases because of the current flow. And there is a minute temperature difference between the coil and the water. That is why there is a heat flow. Heat flow always requires a temperature difference. For the heat to flow, there must be a temperature difference. But the temperature difference between the two systems between which heat flow is taking place, if the temperature difference is very, very small, then the heat transfer is very small. Then the process can be treated as reversible heat transfer. So option A is more appropriate. What is the problem with option B and C? What is the problem with option B and C? Why they are not correct? What about option B? The system receiving heat must be at a constant temperature. No, it is not true. If the water is at 20 degrees Celsius, and slowly but steadily the temperature of water will keep on rising because of the current flow. The current flow will generate heat in the heating coil, and the heating coil will transfer heat to the water. The temperature will keep on increasing. The system receiving heat must be at constant temperature means if there is a phase change in the fluid, if there is a phase change, then the temperature of the system remains constant. So when there is a phase change in the fluid, and if the heat is transferred for the phase change, then the temperature of the system will not change. But in that case, the heat transfer process will be irreversible, isn't it? So that does not make the process reversible. The phase change of the system does not make the process reversible. Getting my point? So the second one is not the correct answer. Similarly, the system transferring out heat must be at a constant temperature. That is also not true. Temperature of the heating coil is not also constant. It will also keep on increasing, and the water temperature will also keep on increasing. So if there is, the third statement is possible when there is a phase change in the surrounding. If there is a phase change in the surrounding, that does not make the heat flow to be reversible process. Both the interacting systems, system plus surrounding, if both the interacting system and surrounding must be at constant temperature, if there is a phase change in both the systems, the system which is receiving heat as well as the system which is supplying heat, if both are undergoing a phase change, then also option D can be true, but that does not make the process reversible. So that is why option A is correct. To make the heat flow process to be reversible, the temperature difference between the two systems should be infinitesimally very, very small. All right? Is it clear? Question number 5 is very, very simple. Question number 5 is very simple. Ashish, is this clear to you? Question number 4. What is the answer to question number 5? Question number 5. Do you know, for same value of Q1 and Q2, for same value of Q1 and Q2, the heat addition and heat rejection, then we can say COP of heat pump will be equal to inverse of thermal efficiency of heat engine. COP of heat pump is reciprocal of thermal efficiency of heat engine, and also COP for heat pump is equal to 1 plus COP for refrigerator. These are true when Q1 and Q2 are same. Similarly, for a reversible cycle, and if T1 and T2 are same, thus source and sink temperature are same, the high temperature reservoir and the low temperature reservoir are having the same temperature, then also COP for reversible heat pump will be equal to 1 upon thermal efficiency of reversible heat engine, and COP for reversible heat pump is equal to 1 plus COP for reversible refrigerator. These relationships are always true, but the condition is whether the heat supplied and heat rejection must be same, or even if the temperature limits T1 and T2 are same, then for a reversible cycle we can have the same type of relationship. What is the correct answer? Option A. Isn't it option A? It is not mentioned, so we can assume it as the constant. We can assume the constant value of heat transfers, the constant values of heat transfer. Option A. Can you just let me know what is the maximum thermal efficiency of a heat engine? What can be the maximum or thermal efficiency of a heat engine? Can it be 1? Can the thermal efficiency of a heat engine be 1? A heat engine can have thermal efficiency as 100% or not? Which heat engine is having 100% thermal efficiency? According to Kelvin-Planck statement, thermal efficiency is always less than 1. The thermal efficiency is always less than 100%. According to Kelvin-Planck statement, the thermal efficiency is always less than 1, but COP for a refrigerator, what is the thermal efficiency? That is W upon Q1. That is the thermal efficiency, and W must always be less than Q1. W should always be less than Q1. W cannot be equal to Q1. Why? Because in a cyclic device, it is impossible to develop a cyclic device which converts the low grade energy into high grade energy completely. That is Kelvin-Planck statement. The low grade energy cannot be completely converted into high grade energy. So the work output cannot be equal to W, cannot be equal to Q1. Otherwise, it will violate the second law or the Kelvin-Planck statement of second law of thermodynamics. But COP for a refrigerator can be less than, can be equal to, can be greater than 1. COP for a refrigerator. What is COP for a refrigerator? Desired output is Q2 and heat input is W. Sorry, desired output is Q2 and work input divided by net work input, Q2 by W. So if we talk about the refrigerator, I had told you in the last class also, if we talk about the refrigerator, there is a possibility that Q2 is equal to W. Q2 is equal to W. So the COP will be equal to 1. Q2 can be equal to W. As well as it can be 40, it can be 60. That is also possible. So Q2 can be more than W, or it can be 60, it can be 40. So Q2 can be less than equal to greater than W. That is why COP for a refrigerator can be less than, can be equal to, or can be greater than 1. What about COP for a heat pump? What about COP for a heat pump? For a heat pump, can it be less than 1? For a heat pump, can COP be less than 1? Or can COP be equal to 1? Can you just let me know about COP for a heat pump? Can the COP of a heat pump be less than 1 or equal to 1? Is it possible? I am waiting for your response. Quickly. बताइए जल्दी जल्दी. Fast. What is COP for a heat pump? What is COP for a heat pump? The COP for a heat pump, desired output is Q1 and work input is W. Q1 by W is COP for a heat pump. Now, if we talk about relation between Q1 and W, Q1 will always be greater than W, isn't it? Because Q1 is equal to, from the first law of thermodynamics, whether it be heat pump or refrigerator, so we know that Q1 is equal to Q2 plus W. So Q1 will be greater than W only. Q1 cannot be less than W. W plus Q2, the total energy entering into the system should be equal to total energy leaving from the system. Are you getting it? So Q1 will always be greater than W, and that is why COP for a heat pump is always greater than 1. It cannot be less than 1. Even it cannot be equal to 1. Why? Because if Q2 becomes 0, if Q2 becomes 0, then Q1 becomes equal to W. But in that case, sorry, is it 1? Is it possible to be 1? COP for a heat pump, can it be possible to have the COP for a heat pump 1? Please do let me know. For a heat pump, it can be equal to 1 also. Why? Because work is a high grade energy, high quality energy, and heat is the low quality energy. So the complete conversion of high grade energy, high quality energy into low grade energy, low quality energy is still possible in a thermodynamic cycle, but the reverse is impossible. The complete conversion of low grade energy into high grade energy is impossible, but the complete conversion of high grade energy into low grade energy is possible. That is why the COP for a heat pump can be equal to 1, can be greater than 1. Right? Can the COP be infinite? Can we have COP infinite? Can there be a possibility to have COP infinite? Can we have COP infinite? COP cannot be infinite. Why? For COP to be infinite, W must be 0. For COP to be infinite, W should be equal to 0. The denominator must be 0. And if W is equal to 0, then the heat cannot flow from low temperature reservoir to high temperature reservoir without any external work. So that will violate, if COP becomes infinite, if a device is having COP infinite, then it will violate the Clausius statement of second law of thermodynamics. What is the Clausius statement of second law? It says that to make the heat to flow from low temperature reservoir to high temperature reservoir, the external work must be done on the system. That is why COP cannot be infinite. But yes, COP for COP for refrigerator can be 0, and that will make COP for heat pump to be 1. COP for refrigerator can be 0. It can be 0. Q2 can be 0. There is a possibility to have Q2 to be 0. Is this clear to everyone? Anybody is having any doubt, you can just let me know. Now the next question, question number 6 on your screen. A condenser of a refrigeration system rejects heat at the rate of 120 kilowatt while its compressor consumes a power of 30 kilowatt. If we draw the refrigeration cycle, I had drawn yesterday also. There is a compressor. Then the working fluid enters into condenser. Then there is a expansion valve and there is a boiler. This is schematic diagram. Work input is here, W in the compressor. Work input is given and the condenser rejects heat to the surrounding Q1 and the boiler takes the heat from. This is how the thermodynamic cycle. This is point 1, then 2, then 3 and then 4. And if we draw this diagram, this is refrigerator, Q1, then Q2, and this is the storage space. And there is a Q in, W in. This is T1. That is the environment. I told you this is the source here and this is the sink. High temperature reservoir is the sink, low temperature reservoir is the source. What is the answer to this question? Now, if you read the question carefully, to get the given parameters, a condenser of a refrigeration system rejects heat at a rate of 120 kilowatt. So, condenser is rejecting heat. This is 120 kilowatt. The condenser is rejecting heat to the environment, that is 120 kilowatt. And it is taking the heat from the storage space. Boiler is taking the heat from the storage space. That is how the refrigerator works. Refrigerator. While its compressor consumes a power of 30 kilowatt, W is equal to 30. So what is Q2? We can find out Q2 from the first law of thermodynamics. From the first law energy conservation applied to the system, Q2 has to be 90 kilowatt, isn't it? The coefficient of performance of the system would be COP for the refrigerator is equal to desired output Q2 upon work input. So that is the refrigeration effect. The question can be to find out the refrigeration effect in terms of ton. The refrigeration effect can also be represented in the form of ton of refrigeration. So Q2 by W, that is 90 divided by 30. The COP will be equal to 3. COP will be 3. And 1 ton of refrigeration effect, 1 ton of refrigeration effect or 1 TR, 1 ton of refrigeration is 3.5 kilowatt. So we can convert this Q2 in terms of ton of refrigeration as well. Do you remember this? 1 TR is equal to 3.5 kilowatt. The next question, question number 7. Everyone, please give it a try. The next one, question number 7. A Carnot heat pump, Carnot means reversible. Heat pump works between 27 degrees Celsius and 327. This is 327 degrees Celsius. Heat pump. And this is 27 degrees Celsius. This is our desired effect, Q1. This is Q2 and this is W. What will be its COP? COP for heat pump, and if it is reversible, that can be written as desired output upon work input, or we can say Q1 by Q1 minus Q2, or we can write it as T1 upon T1 minus T2. What is the answer? What is the answer to question number 7? Question number 7. Yes. So T1 is what? T1 is 327 degrees Celsius. You need to convert it into Kelvin, plus 273 Kelvin. So COP is equal to, T1 is equal to 600 upon, when we talk about the difference, I told you, you can take the difference in Kelvin or degree Celsius, will not create a problem. So 327 minus 27, that will be the temperature difference. So 600 upon 300 will be the COP. The answer will be 2. The COP for Carnot heat pump will be 2. Because it is Carnot heat pump, it means it is a reversible heat pump. That is why the COP will be 2. The next question. Next one. For a given temperature T1, the difference between T1 and T2 increases. The COP of Carnot heat pump. Look, the thermal efficiency, I am talking about reversible cycle. The thermal efficiency is given by 1 minus T2 by T1, or we can say T1 minus T2 upon T1. That is the thermal efficiency. So when the temperature difference increases, as the temperature difference T1 minus T2 increases, the thermal efficiency of reversible cycle also increases, isn't it? As long as the temperature difference increases between the source and the sink, the thermal efficiency will also increase. And we know that COP for a heat pump, and we also know that the COP for a heat pump, reversible heat pump, is 1 upon thermal efficiency of a reversible cycle. So because COP is inversely proportional to the thermal efficiency, that is why COP of heat pump will decrease. COP will decrease. As the temperature difference increases, the COP will decrease. And also COP for refrigerator, that is reversible refrigerator, can be written as COP for heat pump, reversible heat pump, minus 1. If the COP of heat pump decreases, then we can say COP for refrigerator also decreases. So by increasing the temperature difference between source and sink, the thermal efficiency will increase, but at the same time the COP will decrease. So the answer to this question is option B. Is this clear? Is this all clear? Yes, Ashish. Option B, Sagnik. Good, good, good. Question number 9. The next one. A Carnot engine rejects 50%. Again, Carnot engine rejects 50% of the heat absorbed from a source. If we draw the engine, this is Q1, this is heat engine, and heat rejected is Q2, and there is a work output W. A Carnot engine rejects 50% of the heat absorbed from a source to a sink at 27 degrees Celsius. This is 27. What is the source temperature? What will be the source temperature in degrees Celsius? So Q2 is equal to 0.5 Q1 according to the given condition. It rejects 50% of the heat, and if it is rejecting 50% of the heat, work output will also be the remaining 50%. So COP of, sorry, not COP, we are talking about the thermal efficiency will be equal to W work output upon heat input Q1. So that is equal to 0.5 Q1 by Q1. And that can also be calculated as 1 minus, that can also be written as 1 minus T2 by T1. So the question is to find out the value of T1. The question is to find out the value of T1, high temperature reservoir, temperature of the high temperature reservoir. So from here you can find out T2 by T1 is equal to 1 minus 0.5 and T1 is equal to T2 by 0.5. What is T2? First of all, convert it into Kelvin. So that is 300. 300. So 300 divided by 0.5, that is equal to 600 Kelvin. The value of T1 is equal to 600 Kelvin, and 600 minus 273 will be the value of temperature T1 in degrees Celsius. 600 minus 273. What is the answer for question number 9? Are you getting option C? C is the correct answer, 327 degrees Celsius. That is how the questions can be framed and the questions can be solved from this. The next question on your screen, question number 10. We will be having 2 more questions. A heat pump working on a reverse Carnot cycle has a COP of 5. This is beautiful question. Let me know your answer to this question. Everyone, please do let me know your answer to this one. A heat pump working on a reverse Carnot cycle has the COP of 5. If it works as a refrigerator, taking 1 kilowatt of work input, the refrigeration effect will be in kilowatt. Refrigeration effect means Q2. The refrigeration effect. If the COP is 5, we know COP for heat pump is equal to 1 plus COP for refrigerator. So COP for refrigerator will be equal to 5 minus 1, that is 4. And COP for refrigerator, that is equal to 4, can be written as desired output is Q2 by W. If it works as a refrigerator, taking 1 kilowatt of work input, for W to be 1 kilowatt, what is Q2? Q2 becomes 4 kilowatt. Q2 will become 4 kilowatt. Option D. D is the correct answer. Option D. Yes, Sagnik. Option D. D is the right answer. The next one, question number 11. That is also simple. T2 by T1 is how much? The ratio of minimum to maximum temperature, a reverse Carnot cycle working as a heat pump. COP for a heat pump, if it is reversible, then we can say Q1 by W, that is Q1 upon Q1 minus Q2, or we can write it as T1 upon T1 minus T2. So if COP is 7, then the thermal efficiency will be 1 by 7. We can have the thermal efficiency, or we can use this expression only. So 7 is equal to T1 upon T1 minus T2, or 1 by 7 is equal to T1 minus T2 by T1. Or that is equal to 1 minus T2 by T1. The question is to find out T2 by T1. So T2 by T1 is equal to 1 minus 1 by 7. 6 by 7 will be the answer. The ratio of T2 by T1 will be 6 by 7. Isn't it? 6 by 7 will be the answer. Question number 11. C is the correct answer. Question number 12. Question number 12. The efficiency of a Carnot engine is given as 0.75. If the cycle direction is reversed, what will be the value of COP for the Carnot refrigerator? Again, very simple question. So COP for heat pump, you need to find out first. Reversible is equal to 1 upon thermal efficiency of reversible cycle. That is 1 upon 0.75. That is 4 by 3. That is 4 by 3. And COP for refrigerator reversible is equal to COP for reversible heat pump minus 1. That is 4 by 3 minus 1. That is 1 by 3. Or that is 0.33 will be the answer. It is a Carnot refrigerator. You need to find. If the question would have been to find out the COP for a heat pump, then your answer would have been 4 by 3. then your answer would have been 4 by 3. But it is for a refrigerator, then your answer will be 0.33. Again, the question is based on the similar type of concept. The COP of a reversible refrigerator operating between two thermal reservoirs is 4. COP for refrigerator reversible is equal to 4. So we can find out COP for reversible heat pump, that is 1 plus COP for refrigerator, that is 5. The efficiency of a reversible heat engine. So the thermal efficiency of a reversible heat engine will be 1 upon COP for a reversible heat pump. That is equal to 1 by 5. 1 by 5, 20%. 20% will be the answer. Question number 13, 20 will be the answer. And I am giving you one question for assignment. Just give this question a try and do solve it. And if you have any doubt, you can let me know through the Telegram group, which you must be part of my Telegram group. If not, do join me on the Telegram so that you can discuss your doubts with me through the Telegram group. This is your assignment question. Take the screenshot and give it a try at home. And the next class, that is on Wednesday, we will be meeting at the same time and we will discuss the very, very important topic and very, very complicated topic of thermodynamics, that is entropy, at 8 p.m. So do join me for the entropy as well. These are my details. You can get in touch with me through the mail ID which is there on the screen, or you can join me on the Telegram group. The link is mentioned here. All right. So that is all from my side for the day. And what is the answer? No, that is not correct. Let me tell you the answer for this. The answer to the question is option B. B will be the answer. B will be the answer. Ashish, the answer to the question will be B. Okay. So that is all from my side. Stay safe, stay motivated, keep preparing for your upcoming examination with your full dedication and effort, and take care. Good night. See you on Wednesday for the entropy session. That is all from my side. Take care, guys. So let me take your leave. Thank you very much and Jai Hind.